I don't get a lot of takers on these videos, but it's here. Okay, now, you have atoms, correct? And atoms bond. Why do they bond? Anybody? Why do they bond? What part of the atom bonds? Here I have an atom. I have an atom here, and I have an atom here. These are two atoms. What part of the atom bonds? What part of the atom bonds? Be very simple. The inside of the atom or the outside of the atom? The outside of the atom. All right, so the outside of the atom bonds. What's on the outside of the atom? Electrons. So what is the outer part of the atom called? Starts with an E, next word starts with a V, next word starts with an S. 3 words. Electron valence shell, correct? Simple? A little confusing, a little bore-like. Yeah, okay, very good, okay. So, and what is the significance about the electron valence shell before bonding and after bonding? What do they have to look like after bonding as opposed to before bonding?
After the outer shell is full.
No. But thanks for playing, Kate. What does it got to look like? It's got to look like what?
The noble gas.
The noble gas. What aspect of a noble gas? The number of protons? Excuse me?
Electrons.
The valence electrons. Is that what you just said? Is that what you said? Excellent. Excellent. It's got to look like the valence shell of the nearest noble gas, correct? Correct? Yes or no?
Yes.
All right, good. Excellent. Excellent. So when hydrogen bonds, how many electrons is it going to have in a valence shell, and what noble gas will it appear like from the outside?
2 electron and it like helium.
It'll look like helium, correct? All right, good. Now we're going to talk about electronegativity. What's electronegativity, and what does it have to do with any of this?
So, the amount and extraction of electron, outer shell electron.
I need an interpretive statement. I have no idea what he said.
Electronegativity is the energy, attraction energy for outer shell electron.
Say it again.
Attraction for outer shell electron.
No. Close.
The energy required to attract.
No. That's electron affinity.
The ability to attract electrons.
What kind of electrons?
Valence electron.
What kind of electrons? What'd you say?
Valence electron.
No. Valence electrons. Okay. You've got to be specific now. Okay? You got to be specific. What kind? It's like contract language. You've got to be specific. What kind? Bonded electrons, right? Yes or no? All right, so let's look at the big guy first. Okay? All right, here is hydrogen, 1 electron in its valence shell. Here's chlorine, correct?
Yes.
What is the electronegativity of chlorine? Now, don't all jump up at once. You know that you have heart conditions and you don't want to, have a heart attack. But you might want to look in your book, or over there, you have a sheet that you could use. You don't want to go crazy now. I don't want people moving too quickly. Okay, there you go. Only 1 person out of 4 did that. That's good.
Yes.
Okay. So what's the electronegativity of chlorine? A sure sign that you've been doing problems of this nature would indicate to me that you already know what the electronegativity is of chlorine. You know, you should know that. I mean, if you've been doing problems for the test, right, in preparation, you would know that it's 3 to 3.2, right? What does that sheet say, 3.2? Right? And what about hydrogen? 2.2, right? Yes? Okay, good. Now, so what's going to happen with that? What's going to happen?
The chlorine will pull the electron from the hydrogen.
Say it again, Kate?
The chlorine will pull the electron from the hydrogen because it wants it more.
So you're not going to have a covalent bond structure, or it'll yank it away?
No, like, the two elements will share the electrons.
Excellent.
But chlorine wants it more than hydrogen does.
So how do you put that into words where you actually sound like a second-year chemistry student? Did I say that out loud? What a horrible thing to say. Yeah, because of the higher electronegativity of chlorine, you're going to form an asymmetric distribution of charge, aren't you?
Yes.
Right? Well, what's a symmetric distribution of charge? Well, you have this, right? Nice and even. Equal pull, right? So I can split it right down the middle. Half and half, correct? Where this one is going to be like this, more or less. Isn't it? Right? Where you get this asymmetric distribution, correct?
Yes.
And you get this partial negative charge there, right? Because you have a little bit more negative over there, and you're going to have a loss of negative, so it's going to create a little positive, right? And how do you indicate that asymmetric distribution? And what is the asymmetric distribution called?
Polarity.
A what?
Polarity.
Okay. Before that. That asymmetric distribution causes polarity. Correct?
Yes.
Right? But what is the asymmetric distribution called?
Polar.
What is it?
Polar. Oh,
Remember that? A dipole moment. And how do you represent a dipole moment? Are you guys okay? Yes? No?
Yes.
You sure? Okay. There's an arrow, right? Right? Yes?
yes.
You sure? You're positive? I'm going to get something. I'll be right there. You sure? Even though I told you that you have a gumdrop lab, this due, remember? This is due, and it's on line, it's on manufacture. Yes? Right? Didn't I say that? Yes? We did this, right? Okay, so if that's true, then riddle me this, Batman. Let's see if we can find something in here which talks about what I'm talking about. Let's see. Let's see here. This is so exciting. This is so exciting. Let's see. Oh my God, look at this. I even made a nice little handy dandy drawing with everything I just said on it. Look at that. It's amazing. It's amazing that everybody read this so carefully that they couldn't even remember what it is they read. Look at that. Isn't that amazing? Absolutely outrageously amazing. You guys are so stunned because you've been studying so, you're getting burnout. You know, you guys have to stop working so hard, okay? Put your feet up, relax, okay? You guys are way burned out, all right? So this creates a dipole moment, And that dipole moment means that the bond is polar. And if this dipole moment is not canceled, what does that create within the molecule? Is the molecule polar or nonpolar? It's polar because there's an unbalanced, what?
Dipole.
There's an unbalanced dipole. So not only is the bond polar, is there a rule of thumb to determine bond polarity? Now, I didn't ask you to summarize in one sentence or less the Manhattan Project. Right? I'm being very snarky today, aren't I? Look, if the atoms are different on either side of the bond, you're going to have a bond polarity, aren't you? Because you're going to have a difference in electronegativity, correct?
Yes.
Right?
Yes.
Yeah. So bond polarity is not something that's unique. It's very, very common. But a molecule, even though it could be complex, might have very little polarity, correct? If you're going to study biochemistry, the whole concept of polarity is very important within the human body and all the complex proteins that are made. You know, with enzymes, enzymatic activity. What's an enzyme? An enzyme is a giant protein, essentially. What's protein made of? Amino acids. What are amino acids made of? Atoms that have a geometry. That geometry can give rise to what? Polarity. So you can have a molecular polarity, right? You can have a molecular polarity. So the bond polarity is very common. It's the molecular polarity. Dipole moment does not make something polar. It's when there's a dipole moment that's not canceled that creates the polarity in the molecule. Correct? Yes or no? Okay. So we've established when you can have polarity, why you're having bonds. Now let's take a particular model. Let's take a substance. And let's see when we can have a complex molecule that first appears that it's got to be polar, and then when we look at the geometry, we find that, whoa, it's actually nonpolar. And we have to use our knowledge of Vesper and how electron pairs, both bonded and non-bonded, will repel each other to create unique geometries. So let's do this one. Xenon Tetrafluoride. Looks a little weird, doesn't it? We've done this, right? All right, so let's do it. What's the first thing you do? You draw, what you think would be the ball and stick model. Ball and stick model. Okay? Then that's the first step, correct?
Yeah.
Then you list the valences, correct? This is 36, correct? Professor, you want to just stay for this one example? There's a method to my madness.
Yes, absolutely.
Okay? And then, so you're going to subtract off 2 electrons per bond, correct?
Yes.
So that's going to be 8. That's 28. And then you're going to put in what? You're going to satisfy the nearest noble gas. What noble gas is this emulating, the fluorine?
Neon.
Neon, very good. We don't say what? The Voldemort, what's the Voldemort word in my class? I don't like the word what? Octet, I hate that word. the nearest noble gas. Okay? So now we have 1, 2, 3, 4, correct? So we have 24, and then 4, where do those 4 go?
Xenon.
Central atom, okay, good. Central atom. Now that certainly looks polar by the drawing that I made on the board. Could you bring me back, can you bring forward, Kate, a square planar model, please? Now you can see that this might look, so you'd have to actually make the geometry. You'd have to actually make a square planar model. Is that square planar? Not even close. That's okay. I'll tell you, Kate's been working kind of hard, so she's getting a little confused. That's square planar. You have 4 bonds.
2.
And then top and bottom. No, that's not one, but we can make that happen. Give it to me. We can. Poor Kate. Okay. So square planar would look like this. Okay. This is square planar, and you tell me how it's obviously nonpolar. Okay. Here we have it. You ready? Here are each fluoride, right? 1, 2, 3, 4. Correct. And then top and bottom, you have the 2 non-bonded pairs of electrons. Correct? Now, do you see how these opposing fluorines they have dipoles, but they're canceling, aren't they?
Yes.
Aren't they? So those dipoles are canceling. Yes? And then you have the 2 non-bonded pairs up here. What are the non-bonded pairs doing? What's their function? The non-bonded pairs. These non-bonded pairs are keeping these 90-degree angles, aren't they? Because if I took these away, what would happen? No? What would happen if I took these away? What geometry would I get? I would get tetrahedral, 109.5. See that? 109.5 versus 90. You get it? Both the tetrahedron and the square planar are nonpolar, providing these outer atoms are the same. Clear? All right, review part 1 finished. We'll go on to review part 2 in a moment. Clear? You sure?
Yes.
Excellent.